In a time when humanity faces an ever-growing need for energy, and higher and unstable prices for that energy, nuclear power would seem ideal, but the plants are often enormous and take forever to build. Small modular reactors able to be assembled quickly and fill smaller demands may be the answer to the problem. So today we'll be looking at the Small Modular Reactor or SMR concept of nuclear fission, and how they potentially offer cheaper and safer nuclear power, and how they might serve as a better alternative to classic nuclear power plants. This means we'll be digging a bit into both the nuts and bolts of how the reactor designs work, there are many, and how the logistics, economics, and regulatory issues factor in. We will also go through an in-depth explanation of how nuclear power in general works before getting to SMRs. If you know the difference between alpha, beta, gamma, and neutron radiation, what RTG stands for, what a breeder reactor is, and what a moderator is, and can name a few and their pros and cons, feel free to skip ahead. If on the other hand you've heard those terms a lot, but never really got a good intuitive explanation because virtually every video on nuclear power is either a 3-minute video with few details, or a long one that assumes you already know all of that, then grab a drink and a snack. This episode continues our discussion of emerging energy technologies, where we've covered everything from fusion reactors to power beaming satellites to more down-to-earth options like solar and solar thermal. I thought today we would look at a particular type of fission reactor, the Small Modular Reactor, as opposed to our prior more general looks at fission technology or alternative fission fuel like thorium. As usual, see those episodes for more discussion of nuclear power and reactions in general or other power sources. And of course, if you enjoy this episode, don't forget to hit the like, subscribe, and notification buttons. The Small Modular Reactor is one we've been asked to do a focused episode on for years, and has been much on my mind the last 6 months or so. And by good fortune I got approached by a company working on SMRs, Last Energy, which asked me if I was considering doing an episode on it and offered their graphics for the discussion. We will be looking particularly at their systems today near the end. They are a commercial spin-off of the Energy Impact Center, the research institute that developed Open 100, an open-source academic platform for design, construction, and financing of a 100-megawatt pressurized water reactor to prove that nuclear energy can be widely accessible, standardized, and commercialized. Additionally, Brett Kugelmaster's podcast, Titans of Nuclear, conducts interviews and deep dives with folks in the nuclear industry. Kugelmaster is the founder of Last Energy, incidentally, and the Energy Impact Center. I would recommend both Titans of Nuclear and also Rod Adams' Atomic Show podcast for those interested in really getting into the regulatory and economic aspects. Nuclear has definitely seen a bit of a revival, especially outside of the West, and probably at least in part from the current energy crisis, and Last Energy for instance secured reactor contracts in Poland and Romania. Anyway, I picked Last Energy both because good visuals for explaining reactors are in short supply, and because they do seem to have one of the better plans for production and deployment of SMRs. I am not endorsing them, nor are they sponsoring the episode. That and they actually have a small reactor, 20 megawatts. A lot of the SMR designs are hundreds of megawatts and as big as a Walmart, parking lot included, which is still smaller than a traditional reactor facility. They're not alone in that. The Hyperion power module is a 50-ton, 25-megawatt liquid metal-cooled reactor, which is actually quite light in power terms, giving you 2 megawatts of electricity per ton of reactor. And there are many other designs, but between the drawing board and development, the size tends to tick up, and at least partially because size often helps a lot with price and safety. We'll start explaining what all those terms mean in a moment. Now, no discussion of nuclear energy can ever be had without bringing up the dual issue of safety and public fear and regulation. Small modular reactors have both pros and cons in this regard to those matters, and we'll come back to it later. We should acknowledge that nuclear fission is not unique in this. Fusion is often the ideal technology of the future, and maybe always will be, which is maybe why it's so rarely pointed out that they are just as radioactive as fission technologies. They just don't tend to involve or produce long-lived radioisotopes, which is the nuclear waste issue. Power beaming brings up all the problems of space travel, plus the creation of a death ray aimed at Earth as the pipeline for transmission. Coal especially, but oil and natural gas and other chemical fuels have the issue of limited supplies and ecological damage acquiring them and from using them. Solar and biofuels both take up valuable real estate and sunlight, Windmills erect the scenery when not endangering air traffic and killing birds, something most forms of active solar thermal power do too. Needless to say, some of our other favorite high-tech power options like black holes, antimatter, or vacuum energy all have issues of being hard to make and a propensity to wreck things around them, like people, planets, space-time itself, or even an entire region of the universe. There is also the reality that it's a waste of time to talk about any power source as safe or incapable of being weaponized. There is nothing easier to weaponize than cheap energy, by both direct and indirect means. And at the most fundamental level, access to cheap power very literally energizes our nation's industrial sector to the point they can mass-produce conventional weapons and other goods and services to help pay for maintaining and manning those weapons. I like to get that out of the way from the outset, because often fear of nuclear involves reasonable concerns, and other times it gets to a somewhat paranoid and maniacal state, folks wanting ever more and more unreasonable controls against any risk at all. I'm not going to tell folks it's impossible to produce nukes from the thorium cycle, or that an SMR is somehow incapable of causing harm, merely that the technologies under discussion meet reasonable safety standards in comparison to both alternative energy sources and other major technologies. Chasing your tail around for moving goalposts or 100% safety is not a pathway to success or survival, and will punctuate in discussion of certain technologies, aerospace and artificial intelligence being other examples. Now, our goal is not to do a deep technical dive on either the basics of nuclear or any specific reactor design, but it bears repeating how you get energy from nuclear or atomic sources. Those two terms are fairly interchangeable, but you will generally hear me say atomic while nuclear is more popular these days because I've traditionally had a devil of a time pronouncing nuclear. I suspect that term shift is acknowledging that the energy being released in nuclear processes comes from changing the nuclei of an atom, whereas altering the electron shells of atoms in general is involved in more conventional power and chemistry. This difference is also apparent in the fields of nuclear physics and atomic physics, which are quite distinct from each other. There's generally millions of times more energy in nuclei that you can release by messing with it than messing with that electron shell around it though, which is the key source of interest in it. It's not just that protons and neutrons have thousands of times more mass than electrons, and therefore mass energy, but the distances involved. The planetary model of the atom isn't really accurate, but for the moment we'll use that and remember that positive charges attract negative charges and repel other positive charges, and that the force they do that with rises sharply the closer they are, running inverse square with distance. Two protons sitting right next to each other shove very hard on each other, whereas if we move them 1,000 times further away, they would experience only a millionth of that force. Atoms are generally on that scale, with all the protons wound up close to each other and all the electrons far, far away, and it takes energy to bind them all together. So moving those electrons shuffles a lot of energy about, especially in those inner electrons on bigger atoms, but is nothing compared to what is involved in pinning those giant protons together at a fraction of the distance. We discussed more on the inner workings of those and quarks in our Antimatter Factories episode, but all we need for today is to understand that it takes enormous energy to cram more protons into nuclei, and the process of adding protons and neutrons is called fusion. This occurs naturally in very dense and hot places where nuclei can slam into each other trillions of times a second and at ultra-high speeds, as otherwise it's virtually impossible to get two smaller atoms to combine, and most of the matter in the universe is made of those smallest atoms, hydrogen, helium, and their isotopes. Fusion of this sort produces a lot of energy and from a fuel source that is very abundant and thus is very desired. But the trick is that even in our sun's core, this process is so hard to do that your typical hydrogen atom will spend billions of years before being turned into something bigger, which most of the time is a diproton, two protons all by themselves, and these fall apart very fast. Only in supernovae is this actually occurring very fast, and thus a fusion reactor mimicking the sun's core here on Earth would need to have several tons of core material to produce enough power to run a light bulb. Thus, artificial fusion power needs to massively exceed the already insane temperatures and pressure in the heart of a star to be of any use to us, parts of the problem making it work. Sometimes the proton-proton combo though will undergo a switch into a proton, neutron, and positron, the electron's antimatter twin, plus some neutrinos, and this is deuterium. a proton and neutron together, and is an isotope of hydrogen, as is tritium, which is a proton and 2 neutrons. And this is unstable, and after about a dozen years, around half of them will have broken down, and that is true of many atoms, their isotopes, and the period half break down into is the half-life. The type of atom is determined by how many protons it has, that's its elemental number and type, and the neutron count controls what isotope it is. Some are stable, lasting longer than the universe thus far has existed. Others live lifetimes so short they regard a second the same way we frail mortals regard the age of the universe. That's the main nuclear reaction going on in the universe to date, small atoms combining and mostly merging, but often they're spit out a particle, typically an electron, proton, positron, neutrino, neutron, gamma ray, or an alpha particle, which is actually a pair of protons and neutrons, the same as helium. If you're curious, beta radiation is when an electron or positron is emitted and is virtually harmless. When these emissions happen, we call it nuclear decay, and we can derive a small but long-lasting power source by taking a material, or radioisotope, with a decent half-life, say a century, and let it slowly decay, and absorb all that decay energy as heat energy to power a RTG, or radioisotope thermal generator. These aren't super efficient or cheap, but they are ridiculously durable, small, and simple, and thus ideal for low power draw applications in places where repair and refueling are very tricky, like pacemakers and space probes. That's 2 of the ways we generate power from nuclei, and neither has anything to do with fission reactors, except that we often produce radioisotopes in the process and can use them for this. Indeed, that is what radioactive waste is. Materials which have absorbed a radioisotope or had a transmutation of some of its atoms into a radioisotope with a long enough half-life to require long-term storage or disposal, but still short enough to be dangerously radioactive. The longer the half-life of an isotope, the less dangerous it is, generally speaking, as it takes far longer to emit its total radiation. The type matters too, as beta radiation is incapable of penetrating human skin, whereas alpha, gamma, and neutron radiation are all rather dangerous, and indeed alpha and neutron radiation are what we often use to induce fission in bigger atoms. One reason we like being able to process radioactive waste is that the stuff in it is of great value, not just danger. It involves a lot of spent fuel that still has tons of other unspent fuel in it, or some piece of equipment or shielding that now contains a small but dangerous and valuable number of radioisotopes we would like to extract. Stuff getting hammered by radiation tends to wear and break down easier too. The conditions in your typical reactor are rather brutal on materials, even without the problems of radiation, and this is why they often had to be very large, and is part of the problem with making SMRs. Now, fission itself is when a big atom absorbs a smaller piece, like a neutron, and breaks into 2 larger pieces plus some tiny fragments. The reaction we're most familiar with involves uranium-235, one of uranium's more common isotopes, making up 0.72% of naturally occurring uranium on Earth and in this solar system. It has a half-life of nearly 1 billion years, so there's less of it around than uranium-238, which has a half-life of several billion years, though both were probably created in about the same quantities in whichever supernovae or neutron star merger originally made them probably about 6 billion years ago. U-235 is prone to being able to absorb neutrons, assuming they're not moving too fast, and when it does, it will shatter into a krypton atom, a barium atom, and a new trio of neutrons that are moving very fast, indeed too fast for any neighboring U-235 atoms to absorb. This is handy as it prevents new planets with lots of U-235 from melting down or exploding. If you crunch a supply of U-235 down very small though, either by ramming into another chunk of U-235 at very high speed, or doing a precise implosion by surrounding it with explosives and setting them off simultaneously, then you can get your uranium so dense that any neutron emitted by a fission event slows by colliding with another neighboring atom, and is rapidly absorbed by another bit of U-235. That emits 3 more neutrons, which are rapidly absorbed by some more U-235, and this process will result in all that matter undergoing fission in just a fraction of a second. And that's a nuclear bomb, specifically a fission bomb. We use that process to set off fusion in a hydrogen bomb too. And you can power devices by explosions, even fusion bombs, using very large reactors, or use them to push ships like with the Orion drive. And indeed, there are some rare isotopes that, if we had a big supply of them, might allow us to do very small explosions, those that would fit into something more like a very large piston engine. You need a pretty large amount to make a substance thick enough and dense enough that a neutron is unlikely to escape, and this amount is called the critical mass. A more traditional fission reactor works by not compressing that uranium, and instead putting rods of it into a substance the neutrons can bounce off of and slow down, warming that substance, typically water, so the neutrons emerge from the rod after a fission event, as the rods are too small and the neutrons too fast for absorption. Make those rods too big and you get a runaway reaction too, not an explosion, but just a meltdown. For the right size rods, we place a bunch near each other with a moderator in between, again water being common, that slows those neutrons down to be captured in the next rod. We typically have 2 plates of those rods that we can sink into each other, with maximum reactions occurring when they're closest together, and we can control the reaction by carefully bringing them closer or further apart. This can be quite a tricky process, especially because water slows those neutrons at a rate affected by its temperature and pressure, and the water gets heated by those neutrons, and we use this to turn a turbine. Not directly though. We typically cool the entire shielded reactor vessel with different water, which then turns a turbine and makes electricity. Neutrons damage stuff a lot, and uranium rods are very dense and heavy, and a sealed reactor vessel with superheated steam and uranium and neutrons all over it is not conducive to long and perfect performance of mechanical and electronic components. Meltdowns happen when the ability to move those plates apart to slow a reaction breaks, and so the reactor can start feeding into an ever higher rate of reaction, and that's a meltdown. There's a ton of ways to make that less likely that have been developed over the decades. Most reactors predate them, and since we've already spent more time on the basics of nuclear energy than I'd like, see our episode on the future of fission for discussion of those. We also have one other way to make nuclear power by fission, and that's called a breeder reactor, and is the reason why you'll hear some folks say we only have a few centuries of nuclear fuel, and others say we have millions of years worth. Most uranium is U-238, and we separate natural uranium to remove U-238 by centrifuge, enriching the remaining uranium's percentage of rarer isotopes. The chunk left over with fewer of those isotopes is depleted uranium, composed almost entirely of U-238. How enriched a sample is controls how it could be for rapid chain reactions when imploded, for nukes, and thus weapons-grade uranium is very enriched. But uranium-238 can also absorb neutrons, as can thorium-232. Uranium-238 can actually capture unmoderated neutrons, those coming out of a fission event at a couple percent of light speed, and the result of this is getting plutonium, which does not occur naturally, at least in the sense that it presumably does get created in dying stars, but just has too short of a half-life to ever survive planets forming, let alone evolving technological civilizations that can mine it. The thorium breeder reaction does require a moderator to slow the neutrons down to very hot thermal rather than relativistic speeds to be captured, and is thus called a thermal breeder reactor rather than a fast breeder reactor. Breeder reactors let us take a small sample of something fissile and breed a much larger supply of fissile materials from some other material which is otherwise not fissile and is plentiful, or less rare anyway. Again, see the future of fission for more on that topic, but since this is SFIA, I'd feel remiss if I didn't point out that more distant future options potentially open the door to micro-nukes and very tiny nuclear batteries if we can get better and more numerous breeder reactors. You'll have folks ask how small you can make a nuclear bomb or nuclear reactor, and the answers tend to assume uranium or plutonium as the power source, but higher transuranics can do better, and as we discussed in the antimatter episode, if we do find an island of stability, one small enough to run cars would potentially be on the table. That said, when we're talking about SMR, the small part usually means it fits into a fairly large building, and the modular part means individual components can ship on a truck or train car for quick and safe assembly at the site. There are designs for reactors that would fit into a truck or train car that's not really that high tech, they just don't offer much for efficiency, cost, or safety. Same idea, you might build an atomic train, it is entirely doable, but it's much easier to build an electric train and run power down the rails to a much more efficient reactor safely outside a city, as opposed to a train or freight truck that might derail or crash in the middle of a city. Since I live within an hour where the recent chemical car train derailment in East Palestine, Ohio occurred, I am not anxious for every train to have radioactive materials in the engine, and I suspect that incident would do nothing to increase folks' fondness for an atomic train design. But atomic trains have been seriously contemplated. The US Army considered them for off-road trains, for instance, one design being a 54-wheeler that was 572 feet long, handy for circumventing damaged railroad tracks during a war, but really meant for moving cargo in the Arctic over ice. Trying to do this in a car or truck is even harder, as you need to reduce your mass, including your shielding, and in the context of remembering that a very large percentage of cars get involved in crashes damaging enough to mess up the frame or engine or reactor. So again, a small modular reactor isn't about trying to get something that can run in a vehicle, it's about one that you can transport in a vehicle, and so there's no need for it to be complete. Something needing 5 or 6 or 10 cargo containers to move and a few weeks of site prep and bolting together is not a big hindrance to anything other than emergency or military uses, where regular generators can be used instead. You can make a big mobile reactor, even a railcar-sized one that's totally enclosed except for power outlets, but it's not likely to be economical or terribly high-powered, as it only has the railcar surface for getting rid of heat. You're not likely to ever have a reactor that produces more electricity than heat, and some 8x8x20 foot cargo container generating power is limited by not setting fire to its surroundings or melting into slag, radioactive slag, in the process. This is another feature we see in some SMR designs though, for them to have closed-loop radiators rather than the big cloud factories we see on classic nuclear power plants and that require them to be sited near large bodies of water. My wife took our youngest son up flying with her for the first time a couple weeks before I wrote this, and his first reaction on seeing our local power plant miles away over in Perry was to ask if it was a volcano. He is 4 incidentally, but that point's a valid one. We use superheated steam to turn turbines, in nuclear or coal for that matter, and that's generally in the area of thousands of gallons per second or a liter or two per kilowatt hour produced, which is quite the issue if you don't live next to a nice freshwater lake. Seawater works too, but salt is never very friendly to equipment, though desalination is one of the more popular uses of nuclear power. Now, of course, if you live in a desert, a reactor that doesn't need a water supply sounds nice, but why not use solar? And the answer is that solar still doesn't work well at nighttime or in tundras. As usual in our discussion, we're not really interested in a one-size-fits-all power solution, at least from those technologies currently on the table. But again, we are not interested in super small because the point of that is basically something so compact you can stick it into the middle of a city where real estate costs are high and so are power needs. Because unless you can build it out of adamantium and requiring no maintenance or operation, you have to worry about cars crashing into it, reckless hooligans or addicts whacking it with a hammer and spraying the area with superheated steam that was radiating around in the outer jacket, and property values crashing within a mile of it. So again, we are basically always thinking of placement in industrial zones or outside the town, which is more reason why a closed-loop reactor is good. Last Energy, for instance, has an air-cooled plant as part of their design, specifically to allow placement basically anywhere, not just by large bodies of water. There are the better part of 100 major SMR designs out there, and they range from classic reactors to fast or thermal breeders, uranium to plutonium or thorium, water-cooled or molten salt. Water is our classic favorite, but has the problem that its properties vary on temperature and that it turns into steam, which needs to be very high pressure to run through pipes, leading to lots of bursting issues and concerns thereof. Molten salt is popular as an alternative because liquids don't have that big bursting problem, especially when not under significant pressure. We also like to use water as both our moderator and our working fluid, but you don't have to go that way. Again, the moderator's job is to slow neutrons down between uranium rods or fuel pellets, and the working fluid is whatever is carrying that heat off to turn our turbine and make power, which is to say it turns heat into the work of turning that turbine's blades to spin the dynamo that generates electricity. Some reactor designs skip water as a moderator in favor of something like graphite, and indeed the original atomic piles ran this way, being literally a pile of uranium blocks and graphite ones. We can't explore these all today, and each has its own benefits and disadvantages, but we need to look at one to illustrate some of the pros and cons of development and deployment So let's look at the one from Last Energy and their PWR-20 design, which is a 20 megawatt reactor. From the outset, their aim is scalability and rapid deployment, so they made a lot of design decisions based on the idea of easy and available existing supply chains, and the goal of being able to get these installed and running in under 24 months from final investment decision to commercial online date. The design is aimed fairly heavily at their initial base of customers, which in this case includes forced sales to an industrial region in Poland, and a lot of motivation there is making sure you have direct access to a non-fluctuating energy supply that's seated right next to your factories. This is not a theoretical model or design either. They have secured commitments for 10 reactors in Poland and 2 more in Romania expected to come online by 2025, and they do credit a lot of that to opting for off-the-shelf components and going with the more traditional light water reactor we see in most nuclear power plants. They also contract customers under a PPA or power purchase agreement, so the customers are buying energy, not paying for the plant itself. They own and operate the plant, taking on fabrication, delivery, etc., with a cost of under $100 million a plant. I should also note the other well-known SMR is the 470 megawatt reactor Rolls-Royce is developing. Small again being a relative concept, it's aiming for a £1.8 billion cost, which is around a tenth the cost of full-scale plants, but that's a great deal more than the 20 megawatt Last Energy design, or the GE Hitachi 300 megawatt design, or the NuScale 77 megawatt SMR design, and all of those are light water reactors. Light water just means water here, and that is using it both as a coolant and moderator. Heavy water reactors are basically the same but use heavy water, which is where the hydrogen in the water is deuterons, not lone protons, meaning each water molecule has 20 nucleons instead of 18. Though hydrogen deuterium oxide, one deuteron and one normal proton, is often considered heavy water too, or called semi-heavy water. Both are naturally occurring in the oceans, but we can separate and concentrate it, and its density is 11% higher than normal water. It turns to ice at 4 Celsius or 39 Fahrenheit, not 0 or 32, and boils at 101.4 Celsius or 215 Fahrenheit. Off topic, but for extreme high-tech megastructure or terraforming projects, you might use 100% heavy water on a planet you want to have snow at slightly warmer temperatures, like a ski resort hab. More importantly though, it is a better neutron moderator, since it is less likely to absorb neutrons than hit it, just slows them down, whereas light or regular water often absorbs the neutron. Fission reactions are basically a neutron preservation game, so having your moderator suck some up isn't really appreciated. It's not cheap though, but the trade-off is that you can use natural uranium unenriched in a heavy water reactor, but need some enrichment for a light water reactor. For some this is preferable. It's the third most common reactor type, well behind light water reactors, and Canada uses mostly heavy water reactors for instance. Natural uranium is plentiful and pretty cheap, and safe to dig up and handle, so there's no real proliferation concern about power plants using it, whereas SMR designs, by having so many reactors and those needing few people to operate, tend to raise security and proliferation concerns. This is why people will tend to scoff at countries wanting enrichment facilities for power generation though. It is not necessary for a nuclear power plant, but it is for light water reactors, though only a little, way less than weapons grade. However, light water reactors are also smaller and more compact, which probably explains why we're seeing it for SMRs. There are heavy water designs though. Copenhagen Atomic's Waste Burner is a single fluid, heavy water moderated molten salt reactor designed to fit into a leak-tight 40-foot stainless steel shipping container. One of the other things folks are looking at for SMRs is being able to add more modules, so there's a lot to be said for smaller module sizes. If you think you need 500 megawatts, but maybe might need 600 in a few years, or maybe 550, well, it is easier to have smaller modules of 20 or 77 megawatts like Last Energy and NuScale models, and fast deployment and small footprint are big deals too. NuScale delivers theirs in groups of 4 or more, and their renamed reactors, the VOGYR or Voyager, are getting their debut in a couple years, providing power for Utah associated municipal power systems. You also have the big advantage of modularity in construction with SMRs in that so much of the precision work, or work needing radiation shielding, can be done in a controlled factory environment and also opens the door to greater automation. HTR-PM is a small modular reactor that came online in China in 2021 and is not a light water reactor. It's a high-temperature gas-cooled reactor and also a pebble bed reactor. As I mentioned earlier, you don't have to use water or any liquid for either moderating or cooling your reactor, and the first reactors, the old atomic piles, just use blocks of graphite. Pebble bed reactors take a pebble of fissile material, uranium, thorium, or plutonium, and wrap it in a moderator, pyrolytic graphite typically, and ceramics being popular as an outer layer for something usually tennis ball sized. Which isn't pebble sized to be fair, but you can replace a bunch of fuel rods in water, light or heavy, with a bunch of these pebbles and no moderator. Pebble beds cannot have a meltdown, there's nothing to raise or lower or get stuck like with fuel rods. These just naturally react when we dump a bunch of them together, as the moderator and spacing is already baked in. Then we pump a gas through to cool them, something incapable of reacting chemically with the materials inside, like helium, nitrogen, and carbon dioxide, and very definitely not oxygen. The setup in this case has a pair of reactors, each with a thermal capacity of 250 megawatts, both turning a single 210 megawatt steam turbine. Most power generated by nuclear plants, or coal or oil or natural gas or burning wood, is thermal energy, and if you're trying to tell the difference, a megawatt all by itself and abbreviated as a capital M, capital W, is referring to total power output, heat and electricity combined. If you see the MW followed by a lowercase e, that's the electrical power output only, and if it's followed by a lowercase h, that's a megawatt hour, a measure of energy not power, 1,000 times a kilowatt hour, and how much energy you have from a megawatt power source running for an hour, or 3600 seconds or 3600 megajoules. The typical US household uses about 10 to 11 megawatt hours per year, and about 800 households can be supplied for each megawatt of power generation you have. That thermal energy isn't useless either. You can use it for heating locations or desalinating water. We discussed it before for tandem use for running large-scale greenhouse facilities in tundra conditions too, see our episode Colonizing the Arctic. Another design sometimes suggested for SMRs is molten salt, and this comes in two forms, one where molten salts are the coolant, and one where they are also the fuel, where you would use your fissile material and the moderator in the molten salt. The big advantage is that there's no pressure in the reactor even at monstrously high temperatures, no super hot high pressure radioactive steam tearing around all your equipment. Their popularity with SMR designs though mostly comes from them being good for closed nuclear fuel cycles in breeder reactors. Anything that makes it easier to truck something in and flip it on as a big black box needing no maintenance or oversight is nice with SMRs, but of course they have their own problems. Again, see the Future Fission episode for a deeper dive on that. One problem all nuclear has is public relations, which is why I try to do an episode on it every year or two. When it comes to fission, folks with opinions on it generally come in two forms: those who loathe it entirely and probably would under any circumstance, and those who say it fixes everything and has been horribly demonized. So I try to give it a detailed, rational discussion every so often, pros and cons. There's a lot of middle ground, and I'm hardly the only person occupying it, but it can seem like it's A or B a lot, especially on the internet. Indeed, I'm not really neutral either. I am quite pro-nuclear overall, but I don't view it as the magic cure for everything. Generally, I see it as part of a 21st century power pyramid built on it, solar, and hydrocarbons, mixed with opportunistic use of hydro, wind, and geo where it's advantageous. Long term, I figure on fusion or orbital power beaming. Although strictly speaking, I suppose long term, I figure on Hawking radiation. Depends on how long a term we mean, and this is SFIA after all. Scale can get a bit extreme here. I've lived near a nuclear power plant almost my entire life, and they don't hold much boogeyman effect on me, but they do for a lot of folks, and not without cause. You are not crazy or paranoid if the thought of a reactor in your city makes you a bit nervous. Hopefully less so after today, as much of the point of SMRs is to have more widespread use of them. Of course, as with all types of power generation, the devil tends to be in the tiny little details, and it doesn't get much tinier than an atomic nuclei. When we look at the future of nuclear energy or some other part of the energy sector, or really any new emerging technology, folks often get inspired to consider a career in that area and start wondering if it's a good career path, and if so, what they should be learning to forge a career in it. I don't think it will come as a surprise that a good knowledge of math, science, and computer science is invaluable if you want to pursue a career in technology. But learning it can be intimidating, and that's where our friends at Brilliant.org come in. Brilliant has thousands of lessons, from the basics to advanced topics: nuclear energy and reactors, artificial intelligence, data science, neural networks, and so much more. Brilliant's focus on hands-on, fun, interactive learning makes it an amazing tool for learning new skills or keeping your skills sharp while diving deeper into advanced topics. Brilliant can help you build your creative problem-solving skills and stay up to date on the latest innovations. Continual learning is critical to career success, and Brilliant can help with effective, interactive, fun, and bite-sized learning. Brilliant makes it easy to build a daily learning habit, and you can try everything Brilliant has to offer for free for a full 30 days by visiting brilliant.org/IsaacArthur or clicking on the link in the description, and the first 200 people will get 20% off Brilliant's annual premium subscription. So today we had a look at the current and emerging state of nuclear, and folks often worry about its usage in doomsday weapons, but this weekend we'll be looking at some truly mind-boggling weapons able to destroy worlds, wreck galaxies, or even tear apart reality itself in our Sci-Fi Sunday episode, Super Weapons. Then next week we'll contemplate life on giant moons, ones nearly as big as Earth itself or even larger, and how life might arise on such worlds and how we might colonize them. After that, we'll have our monthly livestream Q&A, Sunday, April 23rd at 4 p.m. Eastern Time. Then we'll close out April by returning to Earth and the near future to talk about smart cities and the future of automation in urban environments and how that will change them. If you'd like to get alerts when those and other episodes come out, make sure to hit the like, subscribe, and notification buttons. You can also help support the show on Patreon, and if you want to donate and help in other ways, you can see those options by visiting our website, isaacarthur.net. You can also catch all of SFIA's episodes early and ad-free on our streaming service, Nebula, at go.nebula.tv/IsaacArthur. As always, thanks for watching, and have a great week.